Hi everyone, it's Mr. Glover here. So today the idea is we're going to be focusing on independent events and calculating their probabilities. So let's talk a little bit about the difference between dependent versus independent events, and then we'll talk about how to calculate probabilities for independence. So independent events are they're events that are unaffected by previous outcomes. So I'm going to say that for independent events, um, these are events that are unaffected by prior outcomes. Oops. So for example, you're picking a marble out of a bag, you look at the marble, you put the marble back in the bag. The next time you go to pull one, its probabilities are the same as the first time. If we compare this to a dependent event, it's a little different because dependents are events that are affected. So events that are affected by prior outcomes. And so this would be an example like you draw, well, same thing. Let's say we're drawing from a bag of marbles, but this time we don't put the marble back. Now, the next time we go to pull a new marble, there's less in the bag and all our probabilities have been changed. So let's talk about probabilities. Given the events A and B, the probability of A happening then B, and this is for independent events, is given by probability of A times the probability of B, because B is not affected. We should probably make sure that we write independent only. Oops. We learned last class that if they're not independent, this is probability of B given A, and that's the only real difference. So in solving problems, we need to first ask ourselves whether the events are independent. Then we need to decide which rule to use to calculate our probability. So let's go through some specifically independent event problems. So question one, a card is chosen at random from a deck of 52 cards. It is then replaced by, and a second card is chosen. What is the probability of choosing a jack and then an eight? So this key, or the key to this question is right here, then replaced. Because we're putting the card back, our probabilities will remain unchanged. So we've got a bit of unpacking of information to do. There's 52 cards in the deck, so N is 52 cards in the deck. We have 4 jacks in the deck, and we also have 4 eights in the deck. All right. So if we want to find the probability of jack then 8, we have to calculate the probability of getting a jack and then multiply by the probability of getting an 8. There's 4 of both. So the probability of a jack is 4 over 52. And the probability of an 8 is also 4 over 52. This simplifies to 0.0054 or 59, which is about 0.59%. So roughly 1 in 200 times you pull 2 cards out of the deck, you'll get a jack then an 8. Not incredibly likely, but it's also possible, and it's not like it's a 1 in a million probability. So let's try another one. A dresser drawer contains 1 pair of socks with each of the following colors: blue, brown, red, white, and black. So we've got 1, 2, 3, 4, 5 different colors. Each pair is folded together into a matching set. You reach into the sock drawer and choose a pair of socks without looking. You replace this pair, then choose another pair of socks. What is the probability that you'll get a red pair both times? Okay, and so since there's 5 colors and there's 1 of each, that means the probability of any color, in this case red we're interested in, probability of red is 1 over 5. So if we want the probability of red then red, it's simply given by the probability of red times the probability of red. Since this is independent, because we're replacing the socks, both of our probabilities are just 1 over 5. Which gives us a probability of 0.04 or 4% probability. So that's 1 in every 25 tries, you're going to get red both times. If you start filling in your outcome table, 4% for red, then red, 4% would also be for brown and brown, 4% for blue and blue, 4% for white and white, 4% for black and black. That's 20% of your or your probabilities right there that you're going to get back-to-back colors. It's just that this particular combination is only 4%. All right, let's try some more. A coin is tossed and a single 6-sided die is rolled. Find the probability of landing on the head side of the coin and rolling a 3 on the dice. So as far as the coin goes, there's only 2 outcomes. There's a head or a tail. All right. As far as the dice goes, there's 6 outcomes. There's 1, 2, 3, 4, 5, 6. 6 outcomes. All right. That means for a head or a tail, it's a 1 in 2 chance, so a 50% probability. And a dice, there's a 1 in 6 chance, which is going to be about 18%. Or sorry, 16%. So if we want the probability of getting a head and then rolling a 3, probability of head and 3, the probability is given by probability of flipping a head times the probability of rolling a 3. They're independent events because they're not impacting each other. Probability of getting a head is 1 over 2. Probability of flipping a 3 is 1 over 6. So our total probability is going to be 1 in 12, which is about 8.3%. This multiplication rule can be extended to many outcomes in a row, and it's not exclusive to just 2. So up until this point, we have focused on just 2 outcomes. So like flipping a 7 and flipping a 3. Now we can have a series of things happening, and we can use the same rule where we just multiply the outcomes because they're conditional. Or sorry, because they're non-conditional, they're independent. So a bag of Skittles has 12 red, 10 yellow, 15 green, and 13 blue. Compare the probability of selecting red, yellow, and blue in that order to the probability of selecting 3 greens in a row. Assume each Skittle is replaced after it's selected. Okay, so let's write out what we know. There's 12 reds, there's 10 yellows, there's 15 greens, there's 13 blues. What that means is we've got 50 total. Okay. We are interested in 2 different probabilities. So the first one is the probability of red, yellow, blue. Probability of red, yellow, blue. That would be given by the probability of a red times the probability of getting a yellow times the probability of getting a blue. There's 12 reds, so 12 over 50 is the probability of getting a red. There are 10 yellows, so 10 over 50 is the probability of getting a yellow. And there are 13 blues, so 13 over 50 is the probability of getting a blue. If we multiply these together, we get 0.0125, which is 1.25, so approximately 1.3%, 1.25%. So it's not terribly likely that we're going to get that particular combination. So now let's see what the probability of just 3 greens is. It should be higher because there's more greens in the bag, so they're more likely to be pulled. So the probability of green, green, green is given by the probability of a green times the probability of a green times the probability of a green. This is going to work out to 15 over 50, because there's 15 greens in the bag, times 15 over 50 times 15 over 50. This gets us 0.027, which is approximately 2.7%. So we have more than double the probability that we're going to get 3 greens than red, yellow, blue. And that all comes from the fact that there's more greens than anything else in the bag. All right, let's try some more of these. School survey found that 9 out of 10 students like pizza. If 3 students are chosen at random with replacement, this is all independent stuff. What is the probability that all 3 students like pizza? Okay, so if 9 out of 10 like pizza, that means the probability of liking pizza is going to be 9 over 10, which is 90%, okay? But let's see what happens when we have multiple people that we're surveying, not just one. So the probability of like, and like is given by the probability of the first person liking the pizza times the probability of the second person liking the pizza times the probability of the third person liking the pizza. And so each of these is going to be 9 over 10. And now it's this is where it's kind of hokey. With replacement, we're putting the person back into the pool. Technically, we could randomly select them again. So we could be selecting the same person. But because each person is 90% probability, or has a 90% probability of liking pizza, it's just 9 over 10 each time. That gives us 0.73, 729 actually, which is a 72.9% probability. So almost 3/4 of the time, all 3 people are going to have or like pizza. B, it's a probability that the first 2 students like pizza, but the third hates pizza. So this one's a little bit different. You should probably take note of the fact that probability of liking pizza is 9 over 10. One person doesn't, so the probability of hating pizza is going to be 1 over 10. So probability of like, hate is going to be given by the probability of liking pizza times the probability of liking pizza times the probability of disliking pizza. 9 out of 10 people like the pizza. So that's our probability for the first 2. 1 out of 10 people hate the pizza. So that's the probability for the last one. And this will work out to 0.081, which is about 8.1%. And now, just to kind of clarify, 8.1% is the probability we're going to get like pizza, and then the third person's going to dislike. If we had already surveyed the first 2 people and we just wanted to know what's the probability that the next person dislikes pizza, well, it's 1 over 10. It's always the same. But this particular combination is only 8.1. All right, a couple more questions and we're done. A nationwide survey found that 72% of people in Canada have a washing machine. What is the probability that a randomly selected person does not have a washing machine? Okay, so let's break this down into categories of people. 72% have a washing machine. That means that 100 minus 72%, actually this is the first question, so we can fill it in down below. 100% minus the 72% gives us 28% who don't have a washing machine. Technically, this is a mutually exclusive thing. You can't both have a washing machine and not have one. I guess technically you could have one that's broken, but that's not really part of this problem. So because of that, they both have to add to 100. And I know one of them 72, so the other one is 100 minus 72. Now that we have our probabilities, we can now start constructing the probability of specific events happening. So if 3 people are selected at random, what is the probability that all 3 have a washing machine? Well, if we select 3 people at random and all 3 have a washing machine, that's the probability of washing machine, washing machine, washing machine. That's given by the probability of the first having a washing machine times the probability of the second having a washing machine times the probability of the third having a washing machine. They're all 72%, so they're all 0.72. That gets me 0.373 or 37.3%. So there's a 33% probability that if you randomly picked 3 people, according to this survey, that all 3 are going to have a washing machine. That might seem really low to you. That's just because we need all 3 of them to have one. The chances of any individual person having one is actually much more likely than not. If 6 people are selected at random, what's the probability the first 2 don't have a washing machine, but the last 4 do? Well, what we're looking for is the probability of, I guess I'll call it NW for no washing machine. So no washing machine for the first person, no washing machine for the second person, but then the last 4 do. This will be given by the probability of no washing machine for the first person times the probability of no washing machine for the second person times the probability of a washing machine for the last 4. And now I'm getting kind of tired of writing out 6 things. So what I'm going to do is I'm just going to join my like terms. The first 2 are both probability of no washing machine. So this is the probability of no washing machine, but it's going to be squared. And then the 4 of them at the end, they have a washing machine. So that's going to be the probability of having a washing machine to the power of 4. This equals 0.28 squared times 0.72 to the power of 4. This equals 0.021, which is about a 2.1% chance. So this particular combination is not that likely. There are only about 1 in 50 times are you going to find this combination of people with or without washing machines. And that's where we're going to end things today. So the independent events worksheet is what I'm going to assign. I don't want you to do all the questions. There's 10 questions. I think I'll get you to do questions 1 to 10. We'll say 2 to 10 because I want you to do the evens. 2 to 10, do the even questions. So I'll end this video now. I hope everybody has a good rest of the day, and I'll see you all tomorrow in our chat. Bye for now.